Hi again, further mathematicians. This is exercise 7c. We're going to look at how to find the expectation and variance. Now, of course, we saw that last time, but this time of a variety of different continuous random variables, and perhaps it should say of functions of continuous random variables as well. So that's what the plan is. So let's go on and do it. Now, the mean of a random variable, we've obviously seen before that the mean expectation is written, sometimes say E of x. It's the same thing, but notice this time I'm saying E of g of x. I'm trying to find a function. Now we saw this before actually when we found the variance, and we used the formula that the variance of x was E of x squared minus E of x squared, which sounds the same but isn't. You can see the difference in the position of the squared. So when we did it before, we basically put an x squared into the formula, and so rather than you should recall that to find the integral the E of x, you chuck an x in and you integrate x f of x dx, and to find E of x squared what we did was we integrated x squared f of x dx. So what you kind of realize then is we can now find the E of any function just by doing this, but there's sometimes little tricks you can use to speed things up. So you'll notice there are ways to split this up. So for instance, say I knew E of x squared was equal to 2.7, and they said to me, okay, what's E of 5x squared? Well, using this kind of rule here, you're able just to say, well, that's 5 times the 2.7. I don't need to work that out individually. I just know that you can just take that 5 out as almost like a common factor. So what would that be? That would be 13.5, I think. So there you'll notice this one says E of ax plus c is a of ex plus the c at the end. So you can just take the a out, and then the adding of c just makes it all bigger. Likewise, if I had E of some complicated 3x squared plus 2x minus 5, it's 3 of the x squareds, it's 2 of the E of x minus 5. So using these tricks we can make things a bit quicker. Notice this trick works for E of ax plus c. That's what we just said. But notice the variance has got a special trick where effectively adding on a number to all the numbers doesn't make it more varied, and we've seen this before where adding on a number doesn't make any difference. Notice, however, that when you take out the a for the variance, it becomes a squared, and that's because if you remember that the variance of anything is equal to the standard deviation squared, so it's that squaring that causes the problem. So I would recommend very strongly you write these down. We're going to see these quite a lot. An example then is a 100 centimeter long pipe is to be cut into 2 pieces. The cut is placed at random, so the length of the longer piece has a mean 80. So let's just have a think about this for a moment. Now I suppose it talks to find the mean and standard deviation of the shorter piece. So we want the shorter piece, so I suppose that becomes our variable. But the variable depends on, what's it depends on? It depends on the fact that it's 100 centimeters minus the length of the longer piece. So that's one way to think about this. It says the cut is placed at random, so the length of the longer piece. Yes, this is the way to do it, because the longer piece we know some information about. We know that the mean is 80, so that means E of L is 80. And it also tells us that the standard deviation, so the standard deviation is 2, so I suppose I could write that as the variance of L is 2 squared, obviously because you just square the standard deviation is 4. Now I know this, and I've also got myself a formula. Oops, that's my worst bubble ever. Now I've got my formula, S equals 100 minus L. It allows me to use this formula. I mean, if you like, the A in this case is minus 1. I'm saying A is minus 1 because it's minus x. I suppose plus 100, that's really what we've got here. So if I was to think about this, I should now be able to say, hang on a bit, If I know the expectation of L, I know the expectation of S. It will be minus 80 plus 100. Now, look, see the answer. Its answer is 20. Is that a shock? We're expecting the longer piece to be 80. I'm saying we're expecting the shorter piece to be 20. It's not a shock. But it's interesting that we was able to use our approach to this problem. The standard deviation, now what's the formula? It's 100 minus L. So again, it might be better just to write that more explicitly. It's minus L plus 100. It's minus 1L even, minus 1 times the L plus 100. So my A here is minus 1. So my variance of my S, the shorter piece, now look, A squared, minus 1 times minus 1 is 1. So it's minus 1 squared times by the variance of the other piece, which was 4. And notice that is still 4. And therefore the standard deviation is still 2. And yes, that's what I got all across the board. So I use the formulas when really you could have used a bit of common sense, I suppose, certainly for the expectation. So this next question, f of x equals e of x this time between 0 and log 2. Okay. Just be aware this is the random variable x has this formula. So sometimes it might just say x is or has maybe a PDF of e to the x, and then it'll give it a range of values. So this is quite a cumbersome kind of notation really, but you do see it loads. Interestingly, it doesn't want us to find e of x. E of x, I would just do the integral of x, e to the x. But instead it wants me to find e of y. And it says y is this, and I don't really like the way it's done that. I think I'd prefer it if it had written it in terms of the original thing. Either way, they've done that. So I suppose this is it's like this, but it's kind of not like this. It's e to the minus 2x of what I want. And I suppose the way to, if I want to find e to the minus 2x, which is what I'm after, it's really the integral. If it was e to the x, as I say, you chuck an x in there, but because it's e to the minus 2x, I've got to chuck one of these in of the variable. Of course, the variable is e to the x as well, so it's a bit weird. And I've got to integrate between 0 and log 2. And of course, as soon as you chuck those in, you think, oh, a bit, these two simplify. And when you times powers together, you add the powers, and that effectively becomes e to the minus x dx, which is a lot easier to integrate. But it's just interesting that we've had to do that. Yeah. So anyway, if I integrate e to the minus x, I get minus e to the minus x. And I've got to put in the values 0 and log 2. So it becomes minus e to the minus log 2. Now it might be worth just chucking it in your calculator. I think the answers are probably a half or 2. And if you get an exact answer, it stops you having to actually think about it. Minus e to the minus log 2. Close bracket. Oh, it was minus a half. So this is minus a half when I put that in. And don't forget, then I put the 0 in. And that's e to the 0 is 1. So it's minus e to the 0, which is minus 1. So that's like a plus 1. And I think the answer is therefore a half. I suppose you might be thinking, well, why is this true? Let's see if I can just justify this, why this is there. So it becomes e to the minus. And the minus can be moved up there, which has its advantages, because then it's 2 to the minus 1. And the reason why it's got the advantages is then the e's and the logs next to each other, and they cancel. So that's really like minus 2 to the minus 1, which is minus a half. It does work, but it just goes to show you can sometimes just cheat a bit. Anyway, that's my answer, a half. And this was the answer from the textbook, which I nicked it from. And it also says a half, so that's good. No, they don't on their answer even explain it even better than I did. I think this is the proper answer. So anyway, we've got another example here. It says if the random variable x has probability, well, look at this. For a start, this is saying this is the PDF, and it just says it's 1 over 21x squared. So if you like, the PDF for x is 1 over 21x squared. Now, if I wanted e to the x of this, I would just do the integral of x times by 1 over 21x squared. Notice the way this works. But I want the e of 7 over x, it says to that. And oh, by the way, it's between 1 and 4, so I should have put those numbers in. So therefore, I'm not going to integrate x times it. I'm going to integrate 7 over x times it. Between 1 and 4 dx. Now again, a little bit of algebra. You can quickly see they cancel, so that gives you a 3 on the bottom and a 1 on the top. That cancels with that, so I think it's just x over 3 dx. Now if I integrate x over 3, I get x squared over 6 at the power divided by the power. So I put the 4 in, it gives me 16 over 6. Put the 1 in, I get 1 over 6, which gives me 15 over 6, which is 2.5. So actually quite an easy question, 2.5. And all the time, I suppose, we're thinking to ourselves, you know, what would I do to get e to the x, or in this case it says z. The probability density function of the continuous random variable of z is kz. So we're saying for the z, our formula is kz. And so again, think to yourself, if I want to find e of z, I've got to do the integral of z times by kz dz. What's it? It's between 1 and 3. Now that's to find the e to the z. I notice actually part B wants me to do that. But part A says find the value of k. Now to find the value of k, we just use the idea that the probability equals 1. So let's do that. The integral from 1 to 3 of kz dz this time. That will give me kz squared at the power divided by the power between 1 and 3. So put 3 in, I get 9k over 2. Put 1 in, I get 1k over 2, which is 8k over 2, which is 4k. And of course this all equals 1. So I think k is a quarter. So given that, if I want e to z, it's the integral. Now notice what I've set up here, it's integral from 1 to 3 of z kz. I can now simplify that to a quarter of z squared dz between 1 and 3. Because k is a quarter and z times z is z squared. What's this give me then? Well, a quarter z squared, if I integrate add the power divided by the power, I think gives me z cubed over 12 between 1 and 3. That gives me 3, that's 27 over 12 minus 1 over 12, which is 26 over 12. It sounds like 2.17, I think. It's 2 1/6. Part C goes back to the rule I looked at before. Now, I know now that e of z is, well, 26 over 12. Let's do it properly. Divide by 2 gives me 13 over 6. So if I want 6z plus 5 as a e, I can just do 6 times by the 13 over 6, add 5. Because suddenly that cancels, gives me 18. And find the exact value of this. Now presumably this is a trick. I actually don't think it's a trick. I think I've just got to do it properly. I think I've got to, thinking about it, I've got to use this kind of approach. I want e of this, so I think it's the integral from 1 to 3 of 1 over 1 plus z squared times by a quarter, that's the k, z. And if I do that, oh, I see, yeah, it makes sense now. The quarter I'll bring out to the front, and it becomes z over 1 plus z squared. And you'll notice, if I differentiate the bottom, I get 2z. And that matters because that on the top is a z. So I think it's a quarter of the log of the bottom. But it's not, it's 2z, so I think it's actually an eighth. I'm going to substitute those numbers in. So I've just subbed them in and simplified, and it gives me an eighth log 5. See if you can follow my logic. You see, it's fairly straightforward. you put the numbers in, and you use your log rules to combine these two together. So basically that's it. You're now going to do exercise 7C. It's I think that they're okay. I've got the book open in front of me. Some of them are very easy and some of them are a bit more complicated. So best of luck.